Okay, good afternoon. Thank you for staying. Well, that's fine. My presentation is going to be a lot more visual, so hopefully it's entertaining. So I wish we will have 2 hours or 4 hours to talk about real world use applications of this alternative cement, because I'm lucky to be involved in hundreds and the company even more. So, but we have 15-20 minutes, so I will try to squeeze them all. That's what I'm going to go through, a little bit of the history, and then some of the main applications that I am involved and the team is heavily involved, or the company itself. So let's start with a little bit of history. It was Professor Alexander Klein from UC Berkeley that in 1950, he kind of discovered this compound of the CSA. It was originally, as somewhat described before, intended for shrinkage compensating, to just balance that shrinkage at the beginning of the Portland cement to get some dimension stability. Later in 1970, he partnered with Ed Rice, which became the founder of CTS, to develop the CSA formulations for rapid hardening cement. And subsequently, they start doing a lot of other modifications, and as we have heard today, there's multiple variations of CSA cements. So I want to use this plot just to show where I'm focusing. I don't know if this has a pointer. So it really depends how you play with the compounds, the belite and the calcium aluminate sulfate, and the other compounds that you will fall in one category or the other. I'm going to focus today in the type B and the type K cement, and those are the applications that I'm going to talk through. Let's go back one more step. Patent, the Klein patent in 1964, that was the patent that created the shrinkage compensating concrete. And in fact, 1 year earlier, the first 2 projects were built, and one in Palmdale and another in Lodi. There's segments of these projects that are still in service and still operational. And from there has been hundreds of cases. We saw that plot earlier today, and it's just the schematic of how the shrinkage compensating works. But it's used for type K cement. It is intended to be blended with Portland cement. I don't know, we blended in the 15 to 20% range. And there's multiple applications: warehouses, super flat floors, bridge rehabs, concrete dams, bridge decks, water tanks. Floors, industrial floors is one of the most common application. Data centers, all these data companies, they want these super flat floors with no joints. That's one example built a couple of years ago. There was a 40,000 square feet slabs with no joints. So like what, 200 feet by 200 feet with no joints at all. And that's impressive. At least that's a real cool role use application of this cement. But then there's really different applications. This one in Folsom Dam, right? They were building the spillway. That spillway was going to be submerged, and they needed some type of material with really good stability to prevent the cracking and to prevent expansion and everything. So I'm not going to go to the details of each of the projects, otherwise it will take me a couple of hours. But shrinkage compensating, our component cement, was used in this project. It was a massive $900 million project, and it performed as it was supposed to. It gave us another alternative, and from there, a lot of dams have been using this cement. Then I mentioned that before that the Klein patent, the OST patents, was the one that really created the first CSA alternative for rapid hardening cement, and that's what it's behind our rapid set cement. Multiple applications that which I could have time to pick, but I will pick this one. It was the Chicago flooding in 1992. They were rebuilding a dam, and maybe one of you has even better information and remember what happened in the news. They were rebuilding a dam. The dam failed. A lot of millions of gallons of water started to flood the city, and they had to rehabilitate the containment of that wall, and they literally just pour hundreds of bags of rapid set to harden quickly and to build it back and prevent the city for flooding. And then another emergency, 1994 in California, the Northridge earthquake. That damaged a lot of overpasses, and the reconstruction was going to take a lot of time, especially because the approach slabs were damaged, so in order to reach the overpass damaged segments, they needed the approach slabs. So rapid set was used, BCSA cement was used to rehabilitate the approach slabs, and in fact, they were able to open to traffic the next morning so they could reach those overpasses. And overall, the project finished 72 days before the schedule. And that was the catalyst for, at least in California, and that was the project that really opened the eyes for Department of Transportation in Caltrans to really say, okay, this is a real alternative that we can use. And from there, from 1995 to now, there has been more than 2,000 lanes replaced with BCSA cement and counting. The main spec is 400 PSI in flexural strength at 4 hours, 600 PSI at 28 days, or 550 sometimes, depending which spec. But that's the state that uses the most, and from there, many others adopted the technologies. Again, I can pick many. I was just involved in this one last year in Missouri. Very interesting project because it started in April, finished in November. It started like it's still really cold. It went through the really hot summer, and then it finished in fall. BCS cement and rapid hardening cements are usually or more frequently placed using volumetric trucks, but there's a lot of projects that use ready mix plants, and this was one of those cases. And it's more challenging. It requires a lot more engineering because you are transporting a product for 40 minutes and you are expecting to place it and has the enough workability, but it's also going to set really fast. So the engineering behind this project was really interesting, was very successful. This led to another project in Wisconsin due for next year that is going to be double the size, and those were really interesting. I just want to put something outside of the U.S., right? Because at the end, this is a material, this is technology that is not limited to this country. There's multiple applications and projects that we get involved abroad. This one was in Mexico, a really important highway between Ciudad de Mexico and Querétaro. This was rehabilitated using BCSA, a continuous reinforced pavement. Again, an application not very normal for rapid set, but it performed really well. A lot of challenges of weather especially, and hauling times, because even though there was a plant set on the side, the hauling times and the driving times were up to 45 minutes to 50 minutes. Let's change a little bit now. Not much pavements, now let's go to bridges. That's another application, another real world use that in which we are heavily involved. It could go from structural hinges, link slabs, bridge decks, overlays, partial full depths, approach slabs, patching, you name it, right? This picture over there is the high-speed interchange in Road 8 and Interstate 84 in Connecticut. This was built in 1960. Nowadays, it has a traffic of almost 200,000 vehicles per day. There's not really a good detour for it, so the rehabilitation had to be at night. So basically, they will close at night, do the demolition, cleaning, reconstruction, and opening to traffic at 5 a.m. in the morning. This one took a little bit longer. This was done in a weekend closure. It's still pretty impressive. Highway 280 in San Francisco. It was a 90-hour closure in which they had to reconstruct the entire hinge of the bridge. This was done with a rapid set flowable field mix with specifications that are really strict to 1,000 PSI in flexible strength at 3 hours. It performed and is still performing really well. I took these pictures last week or 10 days ago, not that far from here, Maryland Bay Bridge. This is a project that they are rebuilding the entire bridge sections, and they are building the link slabs using BCSA cement. And they get the bridge around 9 p.m. and they need to open it at 4 a.m. Heavily reinforced, and it performs. It's tricky because that also has a lot of a really tight specification that for permeability and RCPT and resistivity, and I'm going to talk that in a few slides. But that's one more challenge that was added to this project, to the rapid setting mix. Switching to a different application, airports. We are involved a lot in this, and usually the projects we are involved in airports are those ones that the reconstruction play an important role in the economics of the airport, meaning if you shut down that runway, that taxiway, that apron, you are losing millions of dollars. If those airports that are huge, that you have a lot of the tours, that you can close a section and go around, or multiple runways, then that's usually not, that doesn't necessarily need a rapid setting mix. But in the other ones, that's very important. In Chicago Midway Airport, 1994, one of the first projects, 1998, sorry, it has an intersection of the two runways. They reconstruct each runway independently, but the center had to be done, and whatever you do that was going to affect both runways. So it was done overnight, and it was done with rapid setting cement. The other one, the Seattle International Airport, that's a more conventional rehab method, but Seattle is like the big brother of all the airports. They have been doing rehab since 1994 nonstop. They just signed the new contract for the next 3 years. They haven't stopped doing reconstruction using BCSA cement. They have a system and a spec and everything that they know what they are doing. They just get in at night, get out in the morning, nonstop, no issues. A lot of airports have adopted their techniques, their specs, their guidelines, even up to Australia have adopted their methods. Also international projects, Lanyu Airport in Taiwan, one single runway. We can see this aerial picture, or those light color slabs is BCSA cement. We can recognize that because of the change of color. And Melbourne Tullamarine Airport, again, the color will tell us what is BCSA cement, but just imagine shutting down all that apron, that 14 gates for 28 days or so just to replace that damaged pavement. It was really in the middle of the traffic of all those 14 gates. Those slabs were replaced at night without disturbing the operations of the airport. So I want to do like a pause here because I kind of push a lot of projects and applications so far, but let's question about durability and long-term performance. We are talking about alternative cements, we are talking about rapid hardening materials, but how durable they are. These are alternatives and technologies that if they're well designed and well built, they will last forever. I had the opportunity last year to be involved in 2 forensic projects, the Highway 10 in Pomona and the Burbank Airport, one built in 1998, the other one built in 1997. We were able to get in, take a lot of specimens, cores, slabs, and do a very detailed forensic analysis. I'm only putting their strengths just for reference purpose. There's a couple of papers in editing process about it, but we will be able to share that. But the strength tripled in almost 25 to 30 years. So they are still operational. Both the highway and the airport is still operational and fully functional, but the strength tripled in 30 years. Carbonation rates are great, ASR is non-existent, and I can continue so on. So when we talk about real-world uses of alternatives to cement, we always need to question is not only what works now, but it's also like how will this perform in the long term, if it's really economic solution, and at least for BCSA and for us it has been and is very, very well proven. And just to finish the parenthesis, a really hot topic, right? The global warming potential impact of these materials, of these alternative cements. There is a certified EPD value for BCSA, which is like around 70% of the GWP of Portland cement. And for a component, which is our shrinkage-compensating cement, the value is a lot lower. Yes, the component is blended with Portland, so we will need to do the math. But that's also work that we do because we believe it's part of the real-world use of the material, and we need to adapt and we need to be ready for the new tendencies. So let's go back to applications. We stopped talking about the normal alternative cements, both the shrinkage comp and the rapid hardening, and then what do we use with those materials to create new systems like high performance and engineering system, and UHPC is one. We had a couple of sessions in the morning and we had a lot of discussions about the UHPC, but there's an UHPC that is BCSA based that has been in development for more than 5 years. It has been implemented for more than a couple of years at this point. It's a UHPC that will give you the highest strength that is expected, 17 to 19,000 PSI at 28 days, the ductility, the durability, but also the early strength. That is one of the characteristics that other UHP systems might not have. At 1.5 hours to 2 hours, you are already in the 6,000 PSI. So that allows you to open to traffic, to open to loading, and move forward in your projects while still maintaining all the other UHPC characteristics. This was a project in the Dulles and Bridge in Oregon, in which, again, another type of link slab was being built using UHPC, 12 feet long by like 9, 10 inches deep. It was done in winter, which the temperatures were around 48 to 50, and other good characteristics. A lot of UHPC systems really don't work at such cold temperatures because you need that heat to trigger the strand evolution, and we built this in winter time, and it is still performing really well 3 years later, 2 years later. So another application. Another system that we call Liquiloop, which is basically a 3-barrier anti-corrosion protection system. Basically, it coats the rebar to prevent corrosion, it repels water, and it prevents the chlorides to get in. Not going to go into a lot of details, but resistivity values and the RCPT testing values of third party are shown there. Applications are usually bridge decks that are heavily reinforced, but also constructions in marine and coastal environments. And I want to finish with another set of real-world use, more than 5,000 distribution points of our materials, in which a lot of people will use it for all the type of applications that you will imagine. All these products are BCSA-based, not Portland cement, and we will probably spend another couple of hours talking about the applications in vertical, overhead, patching, and repair materials. So just to conclude, CTS has been producing sulfoaluminate cement since the 1960s, is the largest producer of alternative cement, of low-carbon cement in the U.S., multiple application that goes from pavements, both highways and airfield, bridges, structural concrete, flooring, patching, and repairs. Durability and long-term is very well proven, and we will continue trying to prove it.